All right, so now I'm going to go over all of the problems, the number 7 problems. These are all the algebraic proofs. They're not too bad. You basically just combine either the sum of the boundaries or the sum of the degrees with Euler's formula, and then you do some other random step after that, after getting some bounds for m. So in this problem, we have that G is a simple planar graph with all vertices of degree 5 or 6, and we want to prove that G has at least 12 vertices of degree 5. So starting off, we can use the fact that it's a simple graph to tell us that the boundaries are greater than or equal to 3. So we can do 3f is less than or equal to, if I could write, is less than or equal to the sum of the boundaries, which is equal to 2m. So we have f is less than or equal to 2/3 m. And then we can combine this with Euler's formula, which if you rearrange the terms, you can get it so that we have, well, we'll substitute in f, so 2/3 m is greater than or equal to f, which is 2 plus m minus n. And from here, we can subtract the 2/3 m and rearrange the terms to get 1/3 m is less than or equal to n minus 2. And then by multiplying by 3 on both sides, we get the bounds for m, as m is less than or equal to 3n minus 6. And now here is where the fun begins. So we know that the vertices are all degree 5 or 6. So we know that n equals n5 plus n6, and also that 5n5 plus 6n6 is equal to the sum of the degrees, right? Because all of the vertices of n5 have 5, and same with 6, obviously. So we know exactly what the sum of the degrees is equal to, which is exactly 2m. So if we take this equation up here, multiply by 2, there's supposed to be a 2 there, we can combine all of these together, and we can have 5n5 plus 6n6 is less than or equal to 6n5 plus 6n6 minus 12. And then canceling terms, these cancel, those cancel, and you can get n5 is greater than or equal to 12, which is exactly the conclusion we wanted to get originally. So moving on to the next one. So it is, let G be a planar graph in which every vertice has degree greater than or equal to 3, and every boundary has greater than or equal to 4. So we want to prove that there's at least one vertex of degree 3. Now we want to prove something with the degree equaling 3, so we don't want to use the degrees greater than or equal to 3 now. We're going to use the boundary instead. So basically, it's the exact same procedure as the previous problem. So boundary is greater than or equal to 4. So 4f is less than or equal to the sum of the boundaries, which is equal to 2m. So 2f is less than or equal to m. Combining this with Euler's formula, we get that m is greater than or equal to, what is it? What's Euler's formula again? F plus n minus m equals 2. So moving that around, we're going to have to do a lot of extra steps. So let me break this down a little bit. So first off, we'll rearrange it so that we have f equals 2 plus m minus n, but then we're substituting in for 2f, so we need to multiply that by 2. So 2f equals 4 plus 2m minus 2n. So anyway, with that out of the way, back to the original one. We have m is greater than or equal to 4 plus 2m minus 2n. And if we rearrange the things a little bit, we can get that m is less than or equal to 2n minus 4. And those are the fun things. Now, from here, there's not a lot you can think of to do. You're just kind of like, well, so that's where the fun part comes in. We're going to assume that this is all wrong, proof by contradiction. So we're going to assume that the conclusion is false. So if the conclusion is false, then instead of having a degree equal to 3, all degrees are going to be greater than or equal to 4. So with that, instead of using the sum of the boundaries, this time we're going to use the sum of degrees. So 4n is less than or equal to the sum of degrees, which is equal to 2m. So 4n, oops, so 2n is greater than or equal to m. So if we combine this with this, we get 2n is less than or equal to m is less than or equal to 2n minus 4. So 2n is less than or equal to 2n minus 4. So 0 is less than or equal to minus 4, which is obviously false. So since that's false, the assumption we made was false, so the original conclusion is true. Anyway, so here we have G is a simple connected planar graph with all degrees greater than or equal to 6 and less than 6 faces. Prove that G has a triangular face, which is boundary equal to 3. You can assume Euler's formula, which is obviously something we need. So we could either work with the degrees or we could work with the boundary, since we know that it's simple. But we want to do something with the boundary later. So since we want to do something with the boundary later, probably better for us to work with degrees initially. So degree greater than or equal to 3 tells us that 3n is less than or equal to the sum of the degrees, which is equal to 2m. So n is less than or equal to 2/3 m. And then we can combine this with Euler's formula to get n is equal to 2 minus f plus m. And then substituting in m, we get 2/3 m is greater than or equal to 2 minus f plus m. We can subtract to the m's on the left-hand side and rearrange the terms. You'll notice that these start to be very, very similar, and he basically tends to reuse those. And this is basically the same steps we did on, what was it, this one, except instead of everywhere there's an n, there's an f. Ooh, rid of that. So is less than or equal to f minus 2. So m is less than or equal to 3f minus 6. Okay. So now we want to prove that there is a triangular face. So let's assume this is false, because this is similar to the last problem, right? So we have some specific fact we're looking for. We're looking for degree equal 3, boundary equals 4. Boundary equals 3 actually in this case, right? So we're looking for a very specific case. So if we want to prove not an inequality, but we want to prove a single thing, right? In the first one, we were proving an inequality. And then in the next two, we were proving just the existence of something. So if it's a binary thing, well, we can just assume true or false. So again, we're going to assume that this is full should. So assume conclusion false. So if the conclusion is false, then all boundaries are greater than or equal to 4. Okay, so with this, we can get the sum of the boundaries, and skip to that. It's 2f is less than or equal to m. So if we combine that with this, we have 2f is less than or equal to m is less than or equal to 3f minus 6. So 2f is less than or equal to 3f minus 6, or that f is greater than or equal to 6, which is a contradiction because there are less than 6 faces. So since this is false, there we go. The original assumption was actually true, or the original conclusion was actually true. And on to the very last problem. So let G be a connected simple graph. So simple, so the boundaries are greater than or equal to, what do you call it? The boundaries are greater than or equal to 3. And the degrees are greater than or equal to 4. And all faces have boundaries of 3 or 5. So this is kind of similar to the first problem, right? A little bit different, but similar, right? So in this one, we're proving an inequality, and also we have something else that we can use later. So this one is not going to be a proof by contradiction. And also keep in mind that in this one, right, we used the sum of the boundaries to get rid of the f term because we were going to work with n later on. But in this one, we're going to use the sum of the degrees so that we can have f later on. So we can do, so since the degrees are greater than or equal to 4, we have that 4n is less than or equal to the sum of the degrees, which is equal to 2m. So 2n is less than or equal to m. Okay, so then we have good old Euler's formula, right? And we'll need to do a couple operations again with this one. So moving the n to one side, n is equal to 2 plus m minus f, and then multiply by 2. Then we can substitute in m, and we can get m is greater than or equal to 4 plus 2m minus 2f. And then moving around the terms, getting rid of m on one side, rearranging everything once again. We get m is less than or equal to 2f minus 4. And now we're going to do the same thing where f is equal to f3 plus f5. And we also know that the sum of the boundaries, we know the sum of the boundaries because the faces either have 3 or 5. So 3f3 plus 5f5 is equal to sigma boundary, which is equal to 2m. And then from that, we can combine that with this formula. And that's bounds for 2m, so we'll want to do 2m is less than or equal to 4f minus 4, not 4, minus 8. Big brain time. So writing this all out, we have 3f3 plus 5f5 is less than or equal to 4f3 plus 4f5 minus 8. And then get rid of all those terms. And then there's no more of that. Get rid of all of that. That f5 is less than or equal to f3 minus 8. And we want to prove that there is at least 8 more faces of boundary 3 than a boundary 5. And if you look at that, that's the proof.